Hello once again. We are now ready to start section 6.1, which is where we're finally going to start talking about why we are interested in these integrals. Okay. Previous to this, we've just been talking about how to find integrals, where they come from, what rules they have, and we've talked about some specific rules. But now we're going to be more interested in why we talk about integrals. So to kind of take ourselves back to our derivative background, we had our definition of the derivative, that the derivative with respect to x of the function f of x is equal to the limit as delta x approaches 0 of the ratio f of x plus delta x minus f of x, all divided by that delta x term. And this is just, our definition. But what we hopefully were able to see together in chapter 4 was that there's lots more things that we can talk about when using derivatives. And we have only started to scratch the surface in this class. There's all sorts of other tips and tricks to using these derivatives. And so we want to talk about the same thing using our concepts of integration, right? So once again, we have a definition for an integral. The integral is the limit as n approaches infinity, where n is the number of small rectangles. We have some curve, and we approximate that area under the curve by using a bunch of rectangles. And these rectangles are much too big, but the principle still stands. As we let this area, these number of rectangles go to infinity, if we can get a meaningful limit out of here, we call that the integral, also called the antiderivative, coming from the fundamental theorem of calculus, which states that derivatives and integrals are inverses. Now, what are some applications that we can have? Well, we were motivated to find area, but what we want to look at today is we want to talk about this concept of net change, okay, which is going to allow us, using definite integrals, we could turn a rate of change function into what's sometimes referred to as a net change function, where we are able to describe, for example, where are we at? If we knew what rates we were changing to get here, can we, undo that? And the answer, of course, is yes. So here's an example. This is a really important theorem. Actually, this is one of the fundamental theorems of calculus, sometimes called the fundamental theorem of calculus part 1 and 2. I think this is specifically part 1, but don't quote me on that, which says that the position function is the initial position plus a particular integral, where this integral goes from 0 to t. Now, please note this x is what we refer to as a dummy variable. Whatever you want your independent variable to be at the end, we put that as the boundary, and then we just let a dummy variable. And x is real common because we're used to that, but if it makes you feel even better to use something that truly is a dummy variable, might as well use something like p's or something like q's. Okay, so let's say we know a particle's velocity on an interval, aka a boundary, and we also know the initial position. We are well suited to turn this velocity, aka a rate of change, into the original formula. And we're going to use, once again, this is just a carbon copy of what is up here. But notice now I've written down what V is. Okay, so plugging in what I know. I know S of 0 is -3. And I also can integrate the term 16 minus x squared. Of course, we get 16x minus 1/3 x cubed. Notice we're going to evaluate that from 0 to t. Okay? So, same thing as last time. What do we do with this? We split it into one x equals t term, or the upper boundary, and we subtract the x equals 0, the lower boundary. And what you get at the very end is a position function for S. So, as long as I know v of t, the boundary we want to look at it on, and its initial position, and really all you really need is the initial position, we can recover the original S position function. Okay, let's look at another one. The population of prairie dogs, this is coming from your homework, grows according to p prime of t equals 20 minus t over 5. Prairie dogs per month. After 15 months, what is the population? How are we going to find this? Oh, by the way, we also are told a starting population. This is really important to look for. Pretty much all of these questions, I shouldn't say pretty much, all of these questions will give you a starting population. After 15 months, what is the population? Okay, so really what we want to know is what is P of, for example, 15? Okay, well, P of 15 is going to be P of 0, the starting or initial population, plus the net change from the beginning to the 15th month mark. So here is our, and again, I'll call it a velocity. Please note this is not a speed, it's just a rate of change. But the important thing is that we have a start and we have a net change. And that's really what this definite integral shows us. So let's just plug in what we know. We know P of 0 is 50. Plus, we're going to integrate, or actually, we're going to plug in, we know P prime. This is the integral from 0 to 15 of the term 20 minus t over 5. Oh, I apologize. Make sure that you use your dummy variables. And you know what? I'll use p, just for fun. We know this. We can anti-differentiate these two terms. This is 20p minus, what is that going to be? P squared over 10. And of course, we're evaluating this from 0 to 15. This is going to be 50. Oh, let me change colors one more time. This is going to be 50 plus, well, we'll start off with P equals 15. 20 times 15 minus 15 squared over 10. That's the P equals 15 term. And we're going to subtract from that the P equals 0 term, which is 20 times 0 minus 0 squared over 10. Of course, that's the P equals 0 term. Turns out that whole term just equals 0, which is not very interesting. But we get 50 plus, go to our calculator, 20 times 15, 300. 15 squared divided by 10. 22.5. 50 plus 300 minus 22.5. Rounded to the nearest prairie dog. We get over that 15th month period. Sorry, after that 15th month period, we believe there is going to be 328 prairie dogs.